So without any introduction whatsoever, here I'll mute Jeremy out and okay, you are ready to go, sir or ma'am. Can you start your camera?
Well, I have tape over thing. Anyway, let's see. That should be there. And then, and we'll put it in the presentation mode. Can you see the presentation? Well, let's see. That's not what I'm doing now. What am I doing? Start from start. Okay, cool. So let's see, how to secure the future. Yeah, this one's going to be targeted more towards like the average listener, college student, whatever. I'm not going to go too much into the mathematical details, but I'm going to try to point out a bunch of places where anyone watching here can help, even if they're not technically, like, they don't have like the technical background or whatever. Just making sure, can everyone hear me? Tim, you're muted.
Yeah, sorry about that. Yeah, I can hear you fine. Perfect.
So anyways, let's see. This thing's going there. So yeah, the problem is, in the modern era, we're all wage slaves in a sense, and that's kind of like, we all have to work to feed our families, whatever else, and in most cases, that means we have to choose between that and like, oh, if Amazon does something bad, we can't just all boycott Amazon. We don't have that freedom. We're all part of this interconnected system. And I mean, we can do better than this. We're almost at the, technologically at least, at the level of post-scarcity, as I will show with some of my things. Let's see. And there's the wealthy in the world, generally, they have a lot of responsibilities and also incentives to not really help either, even though in principle they have economic independence and they can they have sometimes the freedom to do something, like in the case of Elon, perhaps. So various political systems, they all corrode over time, I would say. Communism is often seen as a power vacuum, and then it requires a strong central government to enforce, and then a bad actor can come in and take control of that. Capitalism, if you have pure free market capitalism, eventually what you get, some people do better than others. They use what they learn and the capital they have to reinforce their position, and you just eventually get a corporate oligarchy, a system of monopolies or other structures. So we don't really have a stable social structure over really long periods of time. And also, legally speaking, we have like no garbage collector. That's a programming term. In programming languages, there's this concept of if you have, and I'll get into more technical stuff soon, but yeah, so in programming, a garbage collector basically, it takes like data that's not being used anymore and frees up the space in the computer. And most governments that exist, most social structures indeed, they have systems that build up complexity, but they never have a way of deciding when a component of that complexity is no longer required or needs to be revised. I mean, sometimes they have a little bit of that structure, but it's like Elon Musk said, it's generally, if you don't have a way of getting rid of old laws that are not necessary anymore, your system will grow more and more complicated until like no one can get anything done by red tape. What we have constructed as a global society is a paperclip maximizer for GDP. And that's not good because there's a whole bunch of other things we might want, like the environment, our own well-being, et cetera. And yeah, I mean, if we don't have our own personal freedom and economic opportunities, then the system is very brittle. It's very top heavy. And if structures at the top fall apart, then we're kind of out of luck. So what solutions do we have? Well, so some people are thinking like transhumanism. If we can change the nature of people, then we can make a capitalist system or a communist system or whatever else that is stable. That's going to take a long time, although there are things we could potentially do, CRISPR, Neuralink, but whatever. A lot of this is controversial, understandably. And I'm sure that there'll be a lot of feedback and conversation in the comments. Constitutional conventions, I mean, that's another thing that we should consider. But anyway, getting down to what we can do technologically outside of all of those social structures that move slowly and change slowly. We should cut out all the noise, focus on actionable intel, test real devices. This has been something that's been absorbed by the APEC crowd very well. We shouldn't generally trust concentrated power structures. Like in the US, generally conservatives trust corporations and not the government. And on the other side, on the liberal side, they trust government but not corporations. Really, you can't technically trust either. I mean, in some sense. Anyway, but we can get our economic independence by technological means, and it's not really new. Like, it's as old as history itself. Hunter-gatherers were technically independent. The Amish are independent with a lower standard of living. The monasteries after the fall of Rome had to be self-sufficient or they wouldn't have survived. So it's possible to be self-sufficient without advanced technology. However, if we want a modern standard of living, we need to work a little bit harder. So there's a whole bunch of areas where people can contribute, even if they don't necessarily know any of these propulsion technologies. So making fully general manufacturing capability, like something that someone could have on a tabletop that can print an iPhone. That's a very complicated problem, but there's a lot of people working on it, as I'll mention a little bit about. Recycling and raw materials processing, that's key. I mean, ultimately the only limited resource is energy, and that's maybe even not true, we'll see. Yeah, and then food, energy production, mobility. If we have all those basics and we can like print an iPhone and print all the modern things that we might need, we're in pretty good shape. We don't have to participate in a greater economy if we don't want to. And we can walk away from any power structure which is becoming hostile. So another important part of this, I think that it was mentioned in previous APECs, and maybe not understood by some of the older people in the crowd, is the open source strategy is very important to what we want to do, especially in the US. So where did I mention the patents? Oh, I'm missing a little bit. Well, anyways, yeah, so in the US, it's first to file. It's not a common thing. A lot of other nations just have first to like post information about or whatever you call it. But the other problem on top of that, though, is that, oh, maybe it was one of these. Oh yeah, the patent dilemma, here it was. So anyway, yeah, you need a provisional patent to prevent others from patenting within the first year. But then if it's something that the military wants not to get out, they can just take it. And if you don't get that provisional patent, someone else who wants that thing can get it, but then the military will just still take it. So that's tricky. And what we do to get around that is this open source stuff. So, I mean, if you're not making any money off of it, they can't really tell you no. If it's fully open source, it's not ideal, but like, I mean, you can't make money off of it while the patent exists. But it's better than the alternative because now the information's out there and people are benefiting from it instead of getting locked up in some like classified thing and never being released. So that's something. And then there's just some useful tips and tricks. SEL4, CubesOS, all these things are, I mean, you can go over them in more detail. Influence mapping is an important tool for understanding the modern world, generally speaking. And there's a few sources of information done in Bradsheet, SEC, Edgar. These things are still untainted by like fake news and other things because there is a legal responsibility with teeth for corporations not to lie in these sorts of information references. Anyways, I'll get into some of the things that we can actually do. So nested greenhouses, and in space, bonsai might be actually a very useful thing. Growing things smaller than they grow in nature may be useful for actually getting like large trees and things growing in space. If you're talking about making some food growing apparatus, because that's going to be at a premium because you're limited by the amount of surface area of your habitat in space. Anyways, ecosystem engineering, we're going to have to get good at that, whether or not we get off this planet. I mean, a quick calculation, and this is extremely conservative. Our ecosystem is worth like 1,000 trillion, even just in pharmaceutical value. So like, that's not accounting all the other positive externalities, like the air that we breathe. So any other species out there in the universe that are looking at us right now, they must think we're insane to destroy literally the most valuable thing that we have that doesn't exist anywhere else in the universe. Just because of combinatorics, to find an equivalent species to something on Earth out there in the universe, you're gonna have to, like, just by probability, you're gonna have to travel some enormous, ungodly, impractical distance, even for whoever is out there now, probably. So, I mean, there's tremendous value in there. And there's a lot of places that have done some interesting work, like Las Gaviotas, Colombia. It's a little town. Oops. Why did it jump? Okay, cool. So yeah, Las Gaviotas, Colombia, they've done a lot of cool work with producing a society which is in harmony with nature. It took them a while to figure it out. But then eventually they found a way to use regenerative agriculture to reclaim savanna into rainforest and produce a profit in the process. There's ways to do this. That we need to figure this out as a species. Anyways, Permian mass extinction, I was going to mention this. Climate change, another, I mean, some people consider this controversial, but could be even worse than any of the predictions, because, I mean, we should be looking also at deep ocean CO2 concentrations. Once that gets toxic, things in the deep ocean will all just die, and that gigantic biomass will release hydrogen sulfide and probably start killing off a lot of things on land at that point. So we don't want to be in that situation, but it looks like we're barreling right towards it, and not many people talk about that. But I mean, maybe people think other things will happen first. But and I mean, for those who like are skeptical about all the climate change stuff, just ask any oyster farmer, not even necessarily like a climate scientist or whatever, just ask an oyster farmer about ocean acidification. They have to literally, when they're growing their new oysters each year, they have to like fix the pH of the ocean water with bases to reduce the acidity of the CO2 in the water before they can actually grow oysters. So there's other ways to find out this information if you think that someone's co-opting the other information, and then you can figure out who's really telling the truth. Anyway, electroculture is interesting. I think that guy, the old scientist on YouTube, was looking at this. Ooh, it jumped again. And that's using electrostatic and electromagnetic fields to affect plant growth. Interesting idea. I think that it's mostly because of the modulation of enzymes and other protein activity in cells, because you can affect that with electrostatic and RF fields if they're strong enough. You can actually modulate, you can modify protein conformation, because the conformational change energies are at, they happen at similar electron volt levels to like radio frequency. So That's something that people should be playing around with a lot more in terms of like cures for things, diseases, etc. You could do a lot of interesting things there potentially. And I don't think people have considered that possibility very much yet. So play around with RF, see if you can like figure out what frequencies different proteins resonate at, if you can get protein samples. That might be interesting. And then there's something else, incinerating toilets. This is a strange thing perhaps, but really if you think about it, the system we have now is even stranger. We take our like sewage and we run it through pipes to a centralized center to treat it. And those pipes are just supposed to last indefinitely. They're infinitely strong, never corrode, whatever. That's not sane. That eventually that system will break. So if we can have waste treatment on site at every like house and home for a reasonable amount of energy, and there's interesting things. There was a technology I saw in Vancouver where they actually separated urine from feces using a conveyor belt at an angle. There's things you can do, and this stuff once you've incinerated it, it's excellent fertilizer, and all of the stuff that would have made people sick is destroyed. So then you can start thinking about growing most of your own food and recycling the waste into more food and continuing that whole process indefinitely, and growing things on site, not wasting like energy on shipping and stuff. Yeah, so there's a lot of interesting opportunities. And actually, what's interesting is the incinerating toilet idea. Bill Gates has been doing that a lot. Anyway, going towards manufacturing. So how do we achieve this sort of capability? There's a bunch of companies that have been working on circuit printing. It's still in a relatively early stage of development, but there are people who have their eyes on it. Polyhedral Carbine, I know Jeremy's mentioned that a lot. I was the one who originally mentioned that to him. Yeah, you can electrolyze iodoform, bromoform, and a bunch of other brominated hydrocarbons to produce polyhedral carbine. And then this material can be reacted into lonsdaleite and other diamond-like carbons for 3D printing purposes. You can do that sort of thing. So there's some really advanced materials in the works. And then printing all of this stuff together is like very important to figure out how to do that. That's something I'm working on in a separate project. Perhaps I'll talk about it in the future if people are interested. Integrated circuit etching. There's someone who's actually done this in their basement, Sam Zaluf, good friend. Like it can be done, it can be scaled down, and people are working on it. Raw materials processing, there's a lot that goes into that. Physical sortation. In China, actually, they have a lot of good methods. They have like magnetic electric sortation, and also they have these spiral separators which separate by density. And then chemical sortation, that's like using chlorine to extract aluminum from sand, and aluminum and silicon. And then also you can use carbon monoxide to harvest asteroids, perhaps in space. You can actually carbon monoxide dissolves nickel and iron at different pressures. So that's most of asteroids. And then you can just collect whatever dust remains. So digesting asteroids, cool idea. More people should play around with that. And then there's the Open Source Hardware Association. If you want to get involved in making us basically have Star Trek replicators, because that's what this is going towards. Anyways, getting towards the energy that I'm sure people are more interested in. So more practical things that people should be looking at are like aluminum batteries. Aluminum is far more available than lithium, and it has a similar or even sometimes better energy density. Not with this particular chemistry that I'm showing here with the aluminum chloride urea solution. But there are other aluminum batteries that have incredible energy density and don't really combust like lithium does. And yeah, I mean, it needs more people looking at it. And there's cheap photocatalytic water splitting. This is fascinating. There's a lot of catalysts that split water. And I mean, one of my favorites is graphitic carbon nitride. That stuff is amazing for splitting water. And you just pyrolyze urea, very cheap urea, to get this material that splits water into hydrogen and oxygen. It does so at maybe 5% efficiency if we're being generous and modifying it the right ways. But but it's so much cheaper than solar panels that it's just amazingly scalable potentially. It also avoids all of the conduction problems of solar panels with the collector grids on the top that have to be optically clear. Heat pumps, simple thing that people can do to modify their homes and stuff. Basically, if you have a heat pump instead of just a direct heater, you can multiply the amount of thermal energy that you're pumping into your house relative to the amount of input energy. It works the same way as a refrigerator, but in reverse. Or I guess it refrigerates the outside, but whatever. Anyways, solid paste fuser. So this thing was, yeah, actually what was interesting about the solid paste patent is place I was working at had a bunch of military folks come in one day, and I was chatting away with a lot of them, and I was like, well, you know what? I don't have the resources to do this, but if you spun some disks really fast, you could generate an amazing magnetic field and make a magnetic bottle for fusion. And then this patent comes out like a few months later. They probably had a bunch of like, I don't know, maybe they added something to the provisional because of that. But that was an interesting conversation that happened. I don't know whether it was related or just coincidence, but we were thinking along the same lines. There's one thing that's important at the like high megavolts to gigavolts field that you're talking about. You're also talking about giganewtons of attractive force between these cones. That's an amazing amount of attractive force. So, I mean, obviously you're gonna have to have some way of repelling these from each other to counteract the attractive force between them. The way that I could potentially see this happening via conventional physics is by electrostrictive relaxation. If the PZT film on the surface has some finite electrostrictive relaxation time, and you're running this thing at a faster, like at a higher frequency AC field, then the electrostrictive relaxation will take too long, and your field starts to repel the PZT surfaces. So that might be a way. I'm not sure if it's sufficient. The other way I had considered, after talking with those folks, I don't know if they're still interested in further modifying their patent, but if you actually take a capacitor, which is also a gyroscope, what you can do is the central capacitor plate, just make that like a sphere or something, and then the other capacitor plate's a torus around that, and you spin that torus up as a, what do you call it? As a gyroscope, and you charge it up to some ungodly amount of electric field. If you also have this be boron doped diamond, or at least you have diamond which has boron doping at the surface of it, then you can sustain crazy electric fields without discharge of that system. And the diamond can actually take the compressive force if you have the boron doped diamond at the outer edge that's charged. So that's a thought. And that thing, that you can get that spinning a lot faster. This PICE patent was, I think the maximum speed they were talking about was at like 300,000 RPM, something like that. But you can get to millions of RPM if you have like a diamond-based spinning gyroscope device, which you're using the electrostatic field to counteract the centrifugal forces on that spinning component. I mean, the original idea behind that design was to get to relativistic speeds. That is going to be challenging just based off of the amount of active correction to the gyroscope that you would need to prevent it from processing at those sorts of speeds. But you can definitely get ungodly magnetic fields out of that, like hundreds of Tesla for a magnetic bottle for fusion. And that's without whatever anti-gravity the PICE patent suggests it needs. So you don't need any of that exotic physics. You could do that with normal everyday physics in principle, and a lot of engineering. Anyway, let's see what else. Yeah, so now we're talking about fusion mechanisms. So lattice confinement fusion, NASA put out an interesting paper, and actually I think it was a week or two ago, I was talking to a guy who worked on the nuclear submarines and also at some nuclear power plants. And he was mentioning NASA was thinking about, well, actually, he and another person I talked to, they both mentioned that NASA was trying to replace the radioisotope thermal generators that they use that have plutonium in them. Because, of course, I mean, that's a proliferation hazard and all sorts of other problems. So the idea was, if you can get lattice confinement fusion to be break even, you could send out probes with that. And we talked about a bunch of different ways that they could do this. So nuclear isomers, oh, I misspelled. Well, whatever. But yeah, you could have nuclear isomers, which you give them a kick with some X-rays or something, and they release a gamma ray. And you can use that to power the lattice confinement fusion. Generally, Bremsstrahlung radiation is not very efficient, but if you have a radioisotope doped into your material, if you have like lithium hydride doped with tritium, that tritium can release electrons, beta particles, and then those, by Bremsstrahlung, will release X-rays. And the other thing is you can dope your lithium hydride with X-ray fluorescent materials. And these X-rays, they'll have a lower interaction cross-section to induce lattice confinement fusion, but also they're way lower energy than gamma rays. So you can have lower performance if the cost trade-off of the energy to produce them is right. So yeah, so the lattice confinement fusion, there may be a pathway to break-even fusion via that method. Even perhaps brute forcing it with an X-ray gun out of like an X-ray machine at a dentist's office or something. You could, there's things to play around with there for sure. So then there's muon catalyzed fusion. I'm sure everyone knows that, or people, the more technically minded people around here would. But that's basically, a muon is like a heavy electron, and because it's heavy, the orbital distance around the nucleus is very small. So then if you have like hydrogen with two muons instead of electrons, like a hydrogen molecule, then the hydrogen nuclei get very, very close together, and they can in fact tunnel into each other and fuse, even at very low temperatures. So muons are really expensive though, and they get trapped on hydrogen, on helium, sorry. And the issue with that is, once they're trapped on the helium, they can't catalyze more hydrogen fusion. One thing that people have looked at is hitting the helium with the right frequency of X-rays or gamma rays to knock off the muons so that they can keep catalyzing the reaction. That is another potential way to break even. And then the other thing that people should look at more is catalyzed fusion using heavy quasi-particles in matter. Typically, those quasi-particles are not as small in terms of their wave function as a muon, but you can have metamaterials in your matter. You can have structured layered things, and those layers in your material can reduce the size in at least one dimension of those heavy quasi-particles. And then those heavy quasi-particles can behave as muons in a lattice that contains hydrogen. So, at least in principle. So there's a bunch of ways. And then definitely check out that guy at MIT, Peter Hagelstein's work. He's doing some really good stuff with Mossbauer coupling that could explain. But yeah, I mean, this is all stuff Jeremy's mentioned that I've talked to him about in the past. So one other thing I think that hasn't come up much, which I think people should check out, is negative entropy systems using absorbing Markov chains. So if you're familiar with thermodynamics, second law of thermodynamics has an implicit assumption that there is no microcanonical ensemble, which is an absorbing Markov chain. And that allows thermodynamics to operate as, that allows the second law to work. If there is a microcanonical ensemble that can be built, which is an absorbing Markov chain, then the second law of thermodynamics cannot apply. And in fact, we may have some examples there's the graphene energy harvester, first thought up at the University of Arkansas, I believe, and now there's a company that's trying to commercialize it. What was their name? They were, I forget, I can put it in the comments later, but anyway, there's the MIT 200% efficient LED. Based off of the emission spectrum of that LED, if you did attach to that LED a multi-junction solar cell, you would probably be able to get at least 60% absorption efficiency, and that would make it over unity via a similar mechanism. Basically, all of these absorbing Markov systems have some things in common. The graphene energy harvester and the MIT LED both have some energy as part of the system that kind of biases the direction that the other energy flows. In the case of the graphene energy harvester, you have a charged flake of graphene between two capacitor plates, and because the graphene plate is charged, when it oscillates back and forth by Brownian motion, by thermal motion, whatever, then the capacitor plates on either side of it pick up a slight AC signal. And it doesn't work without that charge on the graphene. And also the same thing with the 200% efficient LED. It needs a bias voltage on it so that the thermal motion, the phonons in the system can get over the emission limit and actually emit a photon. There's possibly a way to do this in a backyard, scientist sort of way that doesn't require MEMS, micro electromechanical devices. And that's with Neal relaxation or electrostrictive relaxation. And these things, basically, if you have just a solenoid coil with a core, and it's a paramagnetic or paraelectric core, then it has a certain characteristic time scale per unit time. I mean, at a given temperature, it has a characteristic time scale called the Neal relaxation time scale or the electrostrictive relaxation time scale, where at that temperature, the thermal motions in that material disorder the dipoles in that material over time. And if that time scale is different from the resonant frequency of a solenoid built using that coil that material at the center, or capacitor with that material inside it, then you can get some signal that's not at the resonant frequency of that coil system, and you can use a bandpass filter to pick that up and harvest it, in principle. And there's a few free energy devices, quote unquote, that have been seen online, where they also mention that the temperature of the system actually decreases. And that would probably be because it's this sort of electrostrictive or Neal relaxation device. So what's interesting, yeah, I mean, so that you're not destroying, you're not creating energy out of nothing. You're taking it from a disordered state and putting it into an ordered state. It's a negative entropy directly. Anyway, and impedance modulation, this is something I was looking at during my college. Where is it? Sorry. Okay, yeah, impedance modulation. I would say everyone should take a look at this paper by Friedrich Morgenthaler, Velocity Modulation of Electromagnetic Waves. Oh, my screen's still shared, right? I don't see the yellow, the green around the edge.
Yeah, no, we can still see you.
Good. Anyway, impedance modulation. So in this paper, Velocity Modulation of Electromagnetic Waves, Friedrich also accidentally proved that you could modulate the impedance of a wave, of a wave system. And he didn't see it because of the way he formulated his equation. But if you switch out mu and epsilon for gamma and v for velocity and for impedance, not in that order, then you get this other equation here where the new energy is equivalent to this velocity V2 over V1. And then you have this other term, which is 1/2 gamma 2 over gamma 1 plus gamma 1 over gamma 2. What's interesting about this term is it's not time reversible. So if you increase the impedance and then you decrease it again, energy will just increase again. And actually, we found that this only seems to happen at resonance, but this might be another way to break CPT symmetry and extract energy that people can play around with, because, I mean, all you have to do to play around with impedance modulation instead of velocity modulation is you have to vary mu and epsilon inversely to each other instead of directly with each other. And there's potentially materials that do this, like magnetoelectric materials. And there's some composites you can make. Stuff to play around with. Anyway, mobility. This is what people want to hear about, I guess, at a conference like this. But energy is probably useful too. Anyway, so my approach at present to all this research is, I think that gravity actually unifies at low energies. So sometimes they'll show you this like graph where electricity and magnetism unify, and then those unify with the weak force, and then those unify with the strong force. And then people assume that gravity unifies at even higher energies, which that doesn't make much sense to me, because if it unified at such high energies, unless it's some sort of entropic gravity model, then you would expect the graviton to not travel far distances, travel slower than the speed of light, basically have an effective mass. And we don't observe that. We observe a gravity that travels at the same speed as light, over the same distances as light for the most part. So I think it seems more likely that electricity and magnetism unify, then those unify with gravity at low energies, and then all of that unifies with weak and strong force afterwards. So, and then there's also something, flying donut pulses and spatiotemporal optical vortices. Jeremy's mentioned this because I mentioned it to him. These are interesting, and they kind of demonstrate we still don't know everything really. These are Maxwell's equation solutions, which are toroidal in topology or geometry. So one of your fields is going around the ring of the torus, and the other is going along the axis of the torus. And that still obeys Maxwell's equations. It's still, everything's still right-hand rule and everything. But it's just a different way of looking at the photon. I mean, it's if you superimpose it, it's like composed of a bunch of photons that are going at 45 degrees or something out in some direction. Anyway, this shot noise, this is really important for understanding gravity, I think. There's actually a very elegant way of unifying them. And Todd's talked about an equivalent model. Jack Sarfati's talked about equivalent models. Basically, this squeezed vacuum state at the bottom here, that's your graviton. Imagine rotating that around the 2 pi here by 180 degrees, you get the same thing again. That just demonstrates you have something that's spin 2 geometrically. So, and there was another, I think there was a mathematical proof or some physics proof or something that said that if something can be found that is spin 2, then it probably must be the graviton. I think there was some sort of paper along those lines. In any case, a lot of these propellantless drives, like the Woodward thruster, I think at some other conference, the Estes Park, I think, they mentioned that it required second harmonic generation to function. And in fact, a lot of these apparently propellantless thrusters seem to require second harmonic generation. The thing about second harmonic generation is once you have that, you can have vacuum squeezing. So they could be actually graviton thrusters, potentially. Yeah, the other papers have shown that these squeezed vacuum states seem to carry energy and momentum, seem to have interaction cross sections with atoms, like a normal photon does, because they are in a sense a photon. They're just the entangled state of 2 photons, which is an equivalent way of looking at it. What's interesting though is the structure of this squeezed vacuum state is a variable amount of shot noise in the vacuum with a periodic with respect to space and time as the thing travels. And this, if you just take the shot noise as a concept and you imagine that, well, an atom has a lot of electromagnetic waves that it should be emitting, by all the orbiting electrons, but those are all canceling out. Well, consider that if shot noise is a random variable, it probably can't cancel out perfectly. So all atoms are probably emitting shot noise around them as almost like light. And that would spread out with an inverse square law, just like the gravity field does, in the far field at least. So if you superimpose a whole bunch of random shot noise, what do you get? Well, I mean, if you roll 2 dice, the most likely thing you'll get is a 7. And the least likely thing will be a 2 or a 12. And if you roll n dice, you get a binomial distribution, and infinitely many, and you get a Gaussian distribution. And the outliers would be high energy events, and most of the time you get basically nothing. What does that look like? That looks like vacuum. That looks like our definition of the vacuum with quantum fluctuations. So what I submit to you is vacuum refractive index is defined by the shot noise emitted by matter. And a refractive index model, as people have been saying, there's Unzicker's Real Physics, who talks about Einstein's original model of gravity, which was based on a refractive index of space, not a space-time curvature. Refractive index models and space-time curvature models are equivalent. But the refractive index model, in this case, gives you more insight into what's actually going on and why we have a gravitational field, potentially. The other interesting thing is the fine structure constant could be also considered a refractive index in close proximity to matter. It could be considered like the gravitational near field of a particle. And that has a lot of really cool implications that require more study. So, but why do we as observers see a constant speed of light? Well, particles, if the weak and strong forces are, well, let's say refractive index. If we have a variable refractive index in vacuum, then at high energies, what's to say we don't have nonlinear optical properties? Nonlinear optical properties lead to solitons and other behaviors. So what if we can derive the weak and strong forces as nonlinear electromagnetic equations? And I believe that's actually how electroweak unification was done. I'm not so sure about the strong force, but I'm learning still. But anyways, if we can describe these as the particles as nonlinear optical solitons, then they're still affected by this refractive index in space. So the reason that we observe a constant speed of light is because we're simply affected by the local refractive index also. And let's see. It's an interesting concept. I have a few more things to say about that, if I can. But anyways, yeah, so the other cool thing about this is it may actually allow us to unify, it may allow us to understand the limit case of natural laws at the surface of a black hole. Because what happens by Todd Desiato's model is these matter particles actually shrink at the surface of a black hole. So we don't necessarily need strings. We may be able to use classical particles to describe the hair, quote unquote, at the surface of a black hole. I don't know how you get unitarity back out of that, but it offers up some interesting possibilities. Basically, if you have a map of electrostatic field at the surface of a black hole based on the locations of all these particles, then you can have a relationship between that map of field and the places where virtual particles, where Hawking radiation appears at that surface of the black hole. Because, I mean, it's just electrostatic field right there. So you're going to bias what pops into existence. So there's a start of something there. And yeah, it could. The other thing is, let's see, where did I put that? Oh, that's back. Yeah, okay, here it is. No. Sorry, my bad. Okay, yeah, here we are. So looking at the Tic Tac UFO, there's some interesting stuff. I did want to mention something just to clarify. I saw Jack Sarfati and Todd Desiato talking about things. I think they're confused. The loss terms, they both use loss term, but they're using it in different contexts. The loss term in Todd's model describes the state of an atom. The loss term in Jack's model is talking about, well, essentially the transition from electromagnetic radiation to squeezed vacuum states, which is not like a classical electromagnetic. So it's that energy would be considered lost from the perspective of just the electromagnetic wave. But it's really just a conversion term to gravitons, sort of. So it has nothing to do with the size of the atoms. But I just wanted to hopefully help clarify that for them. And on the Xanadu quantum computers, I just saw this recently. I was fascinated. It looks a lot like the bismuth magnesium metamaterial with the cadmium sulfide selenide, whatever it was, nanoparticles at the surface. They have some quantum squeezing resonators, and these provide squeeze states of light, and they go into an interferometer, and that geometry looks very similar to the bismuth magnesium composite with the nanoparticles at the surface for terahertz behaviors. If I had to guess, I would say that surface material just generates a massive quantum volume and just never measures it. And maybe that does something with gravity. I'm not really sure, but it would be interesting to play around with such systems. So one thing that people should know more about is, in terms of Jack Sarfati's model, metals have refractive indices too. They just have a complex number as their refractive index, where the real term is the same sort of refractive index as like glass would have. And then the imaginary term of the refractive index is sort of the loss coefficient, like to conduction losses. And a lot of metals have really high refractive indices, but that doesn't necessarily get us something with a high gravitational refractive index, because if we assume that squeezed vacuum states are our graviton, that may have different interaction cross sections than normal light. Therefore, we can expect that if we want to extend the dispersion relation to include gravitons, we're going to have to take that into account, and it's probably not going to be the same refractive index as for a normal photon. So we have to, that's something that needs taking into consideration. Let's see. Oh, and properties at resonance. Yeah, this is cool. So there's something called a zero index metamaterial, and there's 4-wave mixing. And I want to clarify something that for Jeremy and others, 4-wave mixing really only happens at very high light intensities, because it goes to the third or maybe fourth power, I think third power of the, but I might be wrong on that. But yeah, it goes to some high power of the light intensity. So at low light intensities, the effect is not really present, just by the nature of the order of the effect. And so zero index materials and 4-wave mixing, these are both properties that matter has at resonance. So if we look towards the bottom of the page, this diamond thing that I have here, if we imagine that that's a space-time diagram with the past and future light cone, then if you initiate some event at some moment in time, if you bring your system into resonance, then in principle, you can have access to all the information in that whole time cone within that resonant state. And that's the power of these resonant systems. That's why they can have properties that matter does not normally have at when it's not at resonance. So zero index metamaterials, they really only have a zero refractive index, or appear to have a zero refractive index when they're resonating. Stuff like that. Maybe there's exceptions. I don't think there are, though. So what's interesting about this is you can think of vacuum as a zero index metamaterial for electrostatic fields. Once an electrostatic particle comes into existence, its whole time cone will be filled with that electrostatic field. It is an electromagnetic wave of zero frequency. Therefore, it takes zero energy to emit it. So anything and everything in its future time cone will be able to observe that electrostatic field, even if it falls into a black hole, because the black hole, if that particle is created outside it, can never swallow the whole time cone, as far as I know. Maybe there's some weird black holes with spin or other effects where that could happen. But for a non-rotating, non-charged, normal, everyday black hole, it cannot swallow the whole time cone of that particle. And that's why you would see charge on the surface of a black hole after you throw a bunch of charged particles into it. But what that's also saying is that in some sense, this electrostatic field is traveling faster than the speed of light. But it's not in the sense that you would expect it. So if you're outside its time cone, you're still not going to see it. But so if we take a look at this diagram in the diamond, you can imagine this is this dot represents an electron-positron pair that's created, and this path represents that electron's path through space-time towards an event horizon of a black hole. Well, if you're positioned anywhere in the shaded area, you will always see that electrostatic field, even if it's just directly straight across instantaneously to the edge of that time cone. So that's instantaneous propagation in a sense, but only because you can think of the vacuum as at resonance, quote unquote, with zero refractive index for electrostatic fields. It's a limit case, which does not apply to material, to wavelengths, to frequencies greater than zero. I mean, in a zero index metamaterial, now you can get a non-zero frequency that has apparently zero refractive index within the metamaterial. Similar idea. So what that gets us is something interesting we can play around with. We should be playing around with topological Tesla coils. Basically, that's this in the corner here. There's this idea of a Tesla coil where one of the top loads of the Tesla coil, it's a bipolar Tesla coil where one of the poles surrounds the other and is spherically symmetric. Once you have this geometry, now when you pulse that, you're going to get a near field at the surface, but not necessarily any far field transmission. So that lets you play around with these electrostatic fields in a way that you can squeeze via quantum squeezing. And I'm thinking that'll have some interesting effects, because actually it's really important for warp drives as well. Because warp drives suffer from something called the horizon problem. Basically, how do you project your field in front of your spacecraft? And the way you would do this is with these electrostatic-like fields. So you bring this coil to resonance, and then you squeeze the resonance, so you have some squeeze states. Maybe you do some entanglement, whatever you're doing to it. Near the surface of that Tesla coil, as our first speaker today mentioned, you should expect this electrostatic field to travel faster than light, because it's essentially tunneling, and it's taking advantage of the fact that this electrostatic field is not affected by the light speed, the usual light speed. And that effect obviously falls off in the far field. And in this case, there shouldn't be any far field radiation at all. So I think it goes like exponentially to the relative to the surface or something and dissipates. But anyways, if you have this field that can get faster over the speed of light surrounding the craft, then you can build an actual warp drive, because now you can project a field in front of you, which normally with normal light, you wouldn't be able to do that. So yeah, play around with that, see what you get. It's a simple geometry to manufacture, especially with some of the technologies I'm working on. So now I'm just going to talk about random things that I've also brought up to Jeremy in the past. So I think Elon Musk recently said, if you can find a cube of titanium, like somewhere in the ground, then I'll be interested in looking up, like researching all these aliens and things. Something along those lines. I'm paraphrasing. But we have something like that already. And if anyone knows Elon, let him know about this. So there's these Carbonado diamonds. They crashed probably around 2 billion years ago between South America and Africa, before the continents drifted apart. And you can actually find in Central Africa and in South America deposits of these carbonado diamonds as alluvial traces in sedimentary rock. So what's interesting is upon inspection under SEM, we found some tiny pieces of we found all these like flakes of titanium, little, I think it was about 10, 15 micron rods of titanium embedded in this diamond throughout. There were some other papers that mentioned there were other metals. In the samples I found, I didn't find anything but titanium. I don't know of any natural process. Like there's some people that would say it was from these carbonado diamonds came from a supernova. But if it was from a supernova, I mean, even if it was a reducing atmosphere because all your oxygen is burned away, you're still talking about, you're probably going to get alloys of metals, not just pure titanium necessarily. Unless, no, yeah, I mean, there should be chromium. There should be chromium if this is from a supernova. It should be mixed with chromium and vanadium and other refractory metals. But it's just titanium as far as I can tell. And we also, at the bottom there, the orange is oxygen. So this structure, it might look like rutile that was deposited afterwards, perhaps. But and also, by the way, the striations in the EDS spectra here, or the EDS image, that's because the filament in the electron microscope we were using was about to burn out. So that's that. That's just something that's unrelated to the thing. What you should be looking at is the green versus the carbon background, the purple. So another thing that's interesting is people should be looking at gene drives. They should be looking for messages instead of using like SETI and radio waves. Well, first off, they should be looking at gravitons. If squeezed states and squeezed vacuum can be used for communication and happen to be gravitons, they'll go right through planets, or at least the interaction cross-section will be way different than a photon. So people should be looking for those using balanced homodyne detectors if they're looking for alien communications. But on top of that, we should be looking into gene drives, because there are lots of species that have been around for maybe 500 million years, maybe 300 million years. And if anything visited within that amount of time and was technologically sophisticated enough to edit DNA, they probably would have left at least something. Even if it was just accidental horizontal gene transfer, assuming that species had genes. But yeah, we should see what there is to find in other species, like ginkgo biloba, like blue-green algae, etc. There's a lot of sophisticated signal analysis and signal processing that people have been using in SETI that could be turned towards reading DNA. And that would be interesting to see. So consciousness, the nature of consciousness, people think about this in all sorts of ways. I'm thinking it might be simpler than a lot of people think. Oops, my bad again. It may be as simple as our minds are in some sense a neural net where the outputs of our neural net are also its inputs. That's all it needs to be, really, because so being aware of what we're doing, that's our outputs. So those are just our inputs as well. Now the specifics, I mean, of course there's quantum properties, because otherwise why would sleep evolve as a property? This is something that Jeremy has also mentioned, because I mentioned it to him. So we know there's some quantum processes in the brain, but with or without those, it's still some sort of neural net where your outputs are being reloaded into the inputs continuously. Now that provides some interesting things like, well, this is just another thought, I suppose. Telepathic communication, we're not anywhere near there yet, but if all of our abstract concepts are weights in some neural net, then it may be possible to design a system which basically goes inside your brain with quantum metrology and finds the nearest neighbor structures that would describe a concept and then activates those. There's something called a superconducting quantum interference device That's kind of the closest we have for now. But I mean, now with squeeze states and other new properties, quantum metrology is about to get a lot more advanced. So we should expect that field to be able to really improve towards like reading brains at a distance. And I mean, Neuralink is still better for now, but one day, who knows? But yeah, I mean, if you can find, but the other implication is if you have a telepathic system like this, then it's going to be limited by how similar your neural connections are. So you'll be able to receive information better this way if you already have a matching concept in your brain that you can map to the concept that's being transmitted. Stuff like that. Anyways, some other things. Actually, for Jeremiah, he was just wondering about the magnetic beam device. It was interesting, actually, this morning I was thinking of exactly the same sort of thing. What if you had some wedges that have north and south poles at the inside and outside, and you put these together into a sphere? You have like 8 of these wedges and you stick them together. Well, south pole is supposed to, like, magnetic field lines are supposed to terminate on one of the poles. So if you've trapped this south pole somewhere, what happens? I'm guessing it kind of squeezes out through whatever hole is available. So if you have that magnetic beam device, you've got a bunch of north poles facing a certain direction, and all of that has to come out in one direction. I don't think it goes to a distance or something, but if you have a single hole through this sphere, then all of all the south field or all the north field, whatever's inside, will have to escape through that single hole. So you can probably concentrate an extremely substantial magnetic field into a very small area that way, especially if you have very, very hard magnets. I imagine this configuration will probably destabilize the magnets fairly quickly if they don't have a hole like that. What else? Oh, so people should take a look at Emilio Loretti's work. Kind of quirky friend of mine who seems to be putting a, what do you call it? Knights Templar logo on all of the stuff he builds. I think the Knights Templar are still around. Well, whatever. He has a lot of interesting ideas regarding just classical electromagnetics. There's all these arrangements he's found in the past, which appear to, at least via classical electromagnetics, produce a net force. So, for example, here he has a dipole antenna, F432, where the currents in these wires cause the wires to repel each other, and that produces a force. I thought that was an extremely wasteful device because it's just a radiating dipole antenna. So I thought of an improvement here where you have a quarter wave antenna and you just have a whole cone that's all conductive. And then you have a capacitor plate that like attaches to the end of the cone with a really good dielectric in between. And then you just pump lots of amps into that cone. And you're going to, what you'd probably get is essentially a Z-pinch sort of effect. But you have a slight, because it's a cone, you're going to have a slight angle. And a Z-pinch effect can be very strong if you have a lot of current. So even though you're not, all of your force in a particular direction is, it's like partially canceling out. The force all over, like the force total is very strong. So the part that doesn't cancel should be quite a substantial amount of newtons. If it does indeed work that way, we'll see. So, and this design is nice because it's quarter wave. You can probably encapsulate it and you can minimize the far field radiation, and you can probably throw the Q factor way up there. And my guess is I don't think that these systems violate conservation of momentum. I suspect that most of these systems produce flying donut pulses or spatiotemporal optical vortices, or perhaps the squeezed, like the squeezed vacuum states. Those probably carry some amount of energy and momentum as well. In any case, some weird things to play around with. These are some places people should be paying attention to: Open Source Hardware Association, Hackaday, open source ecology, more towards all of the self-sufficiency technology. Sabine Hassenfelder, of course. Eric Weinstein, Lex Friedman, they're just good. Noam Chomsky, that's more political, perhaps. I hope I haven't rustled some jimmies with politics today, but whatever. So let's see. Yeah, and then some just good YouTube channels. The Hated one here, he's got some really good explanations of how to like do personal security, like internet security properly. ADV China, Lao Wai, those were the guys who figured out the stuff at the Wuhan lab. Good on them. I hope they don't get in trouble with China. Anyway, I think that's just about everything. There's probably some stuff I'm missing, but any questions?
Okay, well, so let me do this. Let me mute you out first. And again, thank you for the presentation, everyone. If you are able to, tune in and give him a big hand.